Welcome, everyone. Today, we're diving into a fascinating area of material science that could revolutionize sustainable energy: ion conductive polymers.
That's right. Specifically, we're looking at polymers that can transport protons or hydroxide ions, which are the heart of devices like fuel cells and electrolyzers.
The core idea we'll explore is that the performance of these polymers isn't just about their chemical makeup, but critically, about their physical structure.
Exactly. This review paper focuses on how organizing these polymer chains, creating what's called a hierarchical or oriented structure, can dramatically boost their ability to conduct ions.
This organization can be achieved through the polymer's own internal interactions or by applying external conditions like magnetic fields or pressure, as shown in this schematic. Correct.
So, how does this organization work in practice? The paper highlights some brilliant examples, starting with liquid crystals.
One study used something called lamellar lyotropic liquid crystals, or LLCs, which are essentially well-ordered, layered structures.
And they found that these lamellar structures provided much more efficient pathways for protons compared to disorganized micellar solutions, resulting in a proton conductivity of 210 millisiemens per centimeter.
Another approach involved polymerizing these liquid crystals to lock in a aligned nanolayer structure.
The results were staggering. The aligned membrane showed a conductivity of 21.9 mscm at 135 degrees Celsius, while a randomly structured version was only 0.8.
This translated to a fuel cell power density that was over 20 times higher for the aligned structure.
Millisiemens per centimeter. Then, researchers even used magnetic fields to align proton channels inside a membrane, which is a really clever way to guide the ions in the right direction.
Let's look at the visuals for those examples. Figure 2a clearly shows the difference between the organized lamellar phase and the jumbled micellar phase. You can literally see the superior highway for protons.
And Figure 2b quantifies that difference in a fuel cell. The power density for the lamellar structure, curve 1, is more than 4 times higher than the micellar one, curve 3.
Now, for the polymerized liquid crystals, Figure 2d illustrates the neat, stacked pathways in the aligned membrane.
Comparing the performance curves in figures 2e and 2f is a night and day difference. The aligned membrane delivers significantly more power at higher currents.
The magnetic alignment technique is also visualized well here. Figure 3b shows how a nano-sponge framework is used to create water-retentive channels that get oriented by the magnetic field.
And the payoff is in Figure 3c. At high temperature and low humidity, very tough conditions for a fuel cell, these magnetically cast membranes, or MMs, massively outperform the standard Nafion membrane.
This brings us to another class of highly ordered materials: covalent organic frameworks, or COFs.
As you can see in Figure 3d, these are crystalline materials with built-in, one-dimensional channels, perfect for ion transport.
And in Figure 3e, we see an example of a sulfonated oligoimide film, which uses liquid crystal properties to self-organize into a highly ordered lamellar structure that's excellent for proton conduction.
Let's talk more about those COFs. By decorating the walls of these channels with sulfonic acid groups, researchers created materials with remarkable proton conductivity.
Indeed, one material called SCOF2 reached a conductivity 20 times higher than a similar, less acidic version, all thanks to the high density of proton-donating groups within its ordered framework.
The paper also discusses a major breakthrough with a low molecular weight, sulfonated oligoimide, which is quite surprising.
It is. Usually, you need long polymer chains, but this material's linear backbone allowed it to form a loosely packed lamellar structure that achieved an incredible proton conductivity of 0.2 Siemens per centimeter.
Now, let's shift from materials that self-organize to ones we organize using external forces.
A great example is a composite membrane made from electrospun nanofibers, which are then compressed.
Figure 4a shows this concept beautifully. When you compress the mat of nanofibers, they buckle and align vertically, creating direct through-plane channels for ions to travel.
This resulted in a membrane with significantly higher proton conductivity, the desired direction compared to a membrane where the fibers were aligned in plane.
A similar principle was applied to anion exchange membranes, which conduct hydroxide ions.
In this case, researchers mechanically stretched the membrane. Figure 4b shows that as the strain increases from 0% to 60%, the hydroxide ion conductivity skyrockets, more than doubling at 60% strain.
Perhaps the most mind-blowing finding is in Figure 4c. Researchers created a 2D nanospace by layering polymer nanosheets.
And in that ultra-confined space, which is only about 4.7 angstroms thick, they discovered that the proton mobility was 100 times greater than in regular bulk water.
That's an incredible discovery, suggesting that creating these 2D water wires is a powerful strategy for designing next-generation material.
Of course, as these materials become more complex and are used in thinner forms, we also need better ways to measure their properties.
The paper points out that new methods are being developed to accurately measure the conductivity of a single nanofiber or a very thin film, which is crucial for understanding how they truly function inside a device.
For example, studies are trying to clarify why the conductivity of a thin film can be different from its bulk membrane counterpart, which has huge implications for device performance.
So, to wrap up, what is the main conclusion of this review?
The overarching message is clear. Mastering the precise arrangement of polymers is the key to unlocking the next level of performance in ion conduction.
Whether it's through molecular orientation or hierarchical structures. Controlling the architecture of these materials allows us to build better fuel cells, electrolyzers, and other sustainable energy technologies.
The reference list here really underscores how active this field has been, especially in just the past 3 years.
Absolutely. The sheer number of high-impact papers cited shows that researchers are intensely focused on designing these structured polymers.
Concepts that were theoretical are now being demonstrated in high-performance devices.
It's a testament to the rapid progress being made at the intersection of polymer chemistry, material science, and electrochemistry.
Looking through these final references, you see work on everything from magnetic field orientation to developing new types of liquid crystalline polymers.
It highlights that there isn't one singular solution. Instead, there's a whole toolbox of techniques that scientists can use to tailor these materials for specific applications.
The findings discussed in this review really pave the way for future breakthroughs.
By continuing to explore and control these intricate molecular structures, we are moving closer to a more efficient and sustainable energy landscape for everyone.